Okay, so thanks a lot for the invitation. It's a pleasure to be here in this school. So today I'm going to talk about new techniques that go beyond Softmax. I'm going to exactly say what that means in a while. In particular, I'm going to focus a little bit on a paper that we are going to present soon at MNLP called Adaptively Sparse Transformers. But so just to convey the big picture about what we are trying to do with this framework, so by now we learned everything about transformers, I guess yesterday, and you did some sequence-to-sequence implementations today in the labs. And so you might have seen by now that transformers are big bulldozers, right? So they are extremely powerful, but they, to me at least, they look a little bit like a brute force solution. They don't seem very intelligent. So in other words, you can't use them for gardening. When they are processing data, they are not going to distinguish, brambles from a rare flower. And so NLP today is leveraging all the power of transformers with all these new Muppet-inspired models like birds, Elmo, and so on, which really looks a little bit like we have Muppets driving these bulldozers. So it's great if you want to get the best scores in the leaderboard for a set of NLP tasks, but they're not giving us a lot of insight about how we can make machines understand human language. So this talk is going to be about sparse bulldozers. What does that mean? So we are delving a little bit in trying to understand what's inside a transformer, what's inside one of these powerful machines, and try to come up with ways that allow us to redesign some of its components in order to discover some structure about language or about data. And so what I'm going to argue today is that sparse modeling is a very powerful technique, a great tool that can allow us to discover such linguistic structure. And it's possible to integrate some of the building blocks making it integrated components in complex systems like transformers. All right, so given this high-level picture, let me take a step back. So most of the things that I'm going to talk about in the class today is not just about a practical application of transformers to a real problem. There's a little bit of some theory behind it, and the central piece of the talk today is all about coming up with transformations from the Euclidean space, denoted by R to the K, so vectors with K dimensions, to the simplex, to the probability simplex. So given a vector with K dimensions, how can we map them to probability distribution with K dimensions? There's a lot of work being done jointly with a number of people, some of them my students, other collaborators. And I'm going to kind of try to give the gist of everything that has been said, that have been done in this space. So what does this have to do with NLP? So the Softmax transformation, I guess you talked about it already when you learned transformers and maybe before, even when you talked about linear models. I think we also had a class on structure prediction using linear models. If you optimize with logistic regression, multinomial logistic regression, you have applied the Softmax transformation in the end, right? So the Softmax transformation is really prevalent in natural language generation. So, for example, we can have a Softmax over the vocabulary to obtain a distribution over words when you are generating words. And we also have a Softmax inside attention mechanisms. If you want to decide where to attend, where to condition, which property of the input to condition, to perform the next decision. So this corresponds to alignment in machine translation, if you want. So in this talk, we're going to talk about new transformations that are similar in a way to what Softmax does, but they are able to capture things like sparsity. We can encode constraints on them, and we can also make them prefer certain kinds of structure. So I'm going to talk a little bit about Sparse Max, a little bit about constraint Softmax and constraint Sparse Max, a couple of slides about Sparse Map. So all these transformations are going to be differentiable, which means that you don't need to apply reinforcement learning techniques or sampling. They are efficient to plug in a neural network, so you can efficiently do a forward step and a back propagation to train the neural network. I'm going to show that we can also learn how sparse this transformation should be for the particular case of transformers. This will be in the end of the lecture. And they can be used either as a hidden layer, like in an attention mechanism, or in an output layer, if you want to draw words from those distributions. Okay, so let's start with the original Sparse Max work. This was a paper that appeared in ICML 3 years ago. And before going into Sparse Max, let me just recap what is Softmax. So the Softmax transformation is basically defining by taking our vector z. So I'm going to denote z as our vector of scores. So z is a k-dimensional vector. And to obtain a probability distribution out of this vector, what we are going to do is very simple. We just exponentiate each coordinate, we normalize, and the result is going to be a probability distribution, which you call softmax of z. Okay, so I guess this should be familiar to all of you by now. So one consequence of this transformation is that because the exponential function is strictly positive, we are never going to have any coordinates of this distribution equal to 0. So the probability distribution that we are going to obtain is going to have full support on these k variables. Okay, so it's going to be a fully dense vector, and we can use them. You can use it both as a loss function if we are working with the cross entropy loss, and we can also use it as part of an attention mechanism. So the second example of a transformation that is also something that we use, routinely, is the argmax transformation. Okay, so this is basically we take our vector z, and we want to return a one-hot vector that has 0 everywhere except in one dimension, and that dimension is the one for which the component of the vector is the largest. Okay, so one way of writing it, and this might be kind of the first example of math that I have in the slides. One way of writing this transformation is by defining this objective function, which is a linear objective on P. P is constrained to be on the probability simplex, and you want to choose P, so Z is the vector of scores, you want to choose the P that maximizes the dot product between Z and P. Okay? And what is going to be the solution of this problem? Does anyone want to say? So by the way, if there is anything that you don't understand in the talk, feel free to interrupt and ask questions. Okay, no answers? So basically, we can choose where to put probability mass, right? So P is our optimization variable. If we have a vector z with scores, the best thing that we can do to maximize this dot product is to put all the probability mass on the largest component of z. Okay, so the result is going to be a P that is 1 in that component and 0 everywhere else. In other words, it's going to be a one-hot vector for the highest score index. Actually, the solution was in the slide. Maybe that's why no one gave the answer. So this is just another way. By now it seems a bit silly. Why am I defining argmax this way? But this is going to make sense in a while. So this is one way of defining the argmax transformation. Okay, so this is a transformation again from the Euclidean space from Rk to the simplex. It just happens that the range of that transformation is always going to be a corner in the simplex. It's always going to be a one-hot vector. Okay, but we can look at softmax and argmax, and this is often used as a hard attention if you want to use it as attention. It's also often used at test time if you want to just generate the most probable words and you don't need the probability distribution over the words. So this is also widely used. Softmax is used when we want something that is kind of a soft version of this, something that assigns some probability mass to all the words. So one drawback of argmax is that it's not differentiable. What do I mean with this? So suppose that we have argmax as a component of hard attention in a model. So let's, for example, take a RNN with attention model for translation, a sequence-to-sequence model with RNN with attention, and let's just replace the soft attention there by hard attention, by argmax. Can we still train this network easily? Why not?
if it's not differentiable, you cannot do the backpropagation.
Yeah, exactly. Right. So we cannot use gradient backpropagation. Why not? Because actually we can. This is a bit incorrect. So it's not that it's not differentiable. It's that the gradient is 0 everywhere, or almost everywhere. So there's going to be a few points, the points where there are ties in the different components of z, where this function is not differentiable. But even in the other points, the gradient is always going to be 0, meaning that if we do a small change on our vector z, like an epsilon change, oops. So if you do an epsilon change on our score vector z, nothing is going to happen on the solution of Max, right? It's still going to be a 1 watt vector on the same point, right? This is why the gradient is 0. Good. Okay. So so what we propose as an alternative is something that is in between Softmax and Argmax. We call it Sparse Max. So it's defined in this way. So we take our score vector z, and we are going to compute the probability distribution p that minimizes this distance between p and z. In other words, we are computing an Euclidean projection of the point z onto the simplex. Okay. So another way of writing this, we can expand the square in this norm. And what we obtain is basically something that looks like this. Instead of minimizing, we can be maximizing. Z transpose P minus 1/2 of the square norm of P. So if we forget about this term in red, this is exactly what I had before when I described Argmax. So we can regard this as a kind of a regularized version of Argmax. Okay. So is this clear why this is kind of one of the most important parts of the talk? So if you don't understand why these two things are the same, or why this is an Euclidean projection of z onto the simplex, this is the time to ask. Yeah.
I understand. I thought z was in the space R over k,
Mm-hmm.
and is in the space delta over t minus 1. How is the subtraction possible?
How is the what?
How is the difference possible?
So the dimensionality, so we are parameterizing the probability distribution as a vector with k dimensions. It's just that you are constraining that vector to sum to 1 and all the elements to be greater than or equal to 0. So z and p, so this simplex is embedded in the RK Euclidean space. Does that make sense?
Yes, but the difference is still between two different spaces, because p is in k minus 1 and z is in k.
Ah, okay, I see. Okay, let me do a clarification. So this denotes that the simplex is k minus 1 dimensional, because there is a linear dependence between the different probability distributions, because they need to sum to 1. So this delta k minus 1 is actually an object that is embedded in the RK Euclidean space. So we can still represent it as like if k is 5, z is a vector with 5 dimensions, and p is a probability vector with 5 dimensions as well. This is just a notational thing. Yeah, thanks for pointing it out. Yes?
Can you turn to the next slide? Yeah. Why is the p square not? I mean, why you using the L2, the L2 organization, and not the L1? Because L1 have the probability to make it more sparse.
Mm-hmm. Yeah. So I get that question a lot. Let me try to explain what this means. So this is this L2 norm here is a projection of z onto the probability simplex, an Euclidean projection. And this projection, in general, it is sparse. So if you want to visualize it, suppose that I'm holding a simplex here, and point z is somewhere where you are. If you project it in a particular direction, it's going to be, as you move further and further away, it's becoming more and more likely that we are hitting the boundary of the simplex. For example, a corner or an edge of the simplex. So the Euclidean projection is already sparse. And why is it sparse? So if you think about the way you parameterize the simplex, one way of writing this constraint is to say that the L1 norm of P is 1, right? So you are fixing the L1 norm of P and saying also that P is greater than or equal to 0. So all the coordinates of the distribution are greater than or equal to 0. So the L1 norm is already somewhere here in this constraint space, right? This is also, it also explains why these projections are going to be sparse. So if we had like if instead of the L2 norm, we had the L1 norm, it would make sense because the L1 norm of P is always going to be 1, right? For P's that belong to the simplex. Does that make sense? Is this yeah?
Why do we want sparse distributions?
Say that again?
Why do we want sparse distributions?
Okay, so this is what I'm going to motivate throughout the talk. What we are trying to achieve here is basically having these transformations that allows us to select only a certain number of variables and not wasting probability mass for all of them. And we are going to see throughout the talk that this can lead to better interpretability, that we can, by looking at the variables that got non-zero probability, we can also get some information about where was the model attending when it came up with the decision, and so on. Yes?
I have a question about, what's the difference between the Gumbel Softmax and the Sparse Softmax?
So Gumbel Softmax is different from, so the difference between Gumbel Softmax and Sparse Max?
Yeah, right. What's the, what's the motivation? What's the difference about their motivation?
So Gumbel Softmax kind of arises because typically you are using something like a argmax inside your model, like for attention or as a latent component, and then you cannot differentiate argmax. And so one way of doing that is to represent argmax as a, either argmax or sometimes you also use it when you have a stochastic model, a stochastic node, and you want to define a sample from that node, right? And one equivalent way of sampling from a multinomial distribution is to write it as the sum, as the argmax of the scores plus a sample of a Gumbel noise, right? This is not what we are doing here. So yeah, and the Gumbel Softmax arises because we are kind of softening that Gumbel distribution. Okay, so what we're going to see today is that this projection tends to be sparse. The intuition is that as I'm holding the simplex here and the point moves further away, there's going to be it will tend to hit the boundary of the simplex, but we are going to see that despite it's being defined in a very different way from softmax, there's a lot of properties in common between sparse max and softmax, and I'm going to tell you about that. So before I proceed, let's analyze a little bit what the solution of that optimization problem that I had in the previous slide looks like. So it turns out that if you address this problem here, finding the minimizer P that minimizes this quantity while it's constrained line the simplex, if you write the Kkt conditions of this optimization problem, I don't know if how many of you are familiar with Kkt conditions and optimization in general? Or let me rephrase, who doesn't know what Kkt conditions are? Okay, like a lot of you. So, so this is a technique that is used to solve an optimization problem, okay? And what I'm showing here is that we can mathematically show that the solution P star of that optimization problem that I had in the previous slide takes this form. So the ith component of P, the ith component of sparse max of Z, is going to be either 0 or something that is the score Zi minus a constant. Let's call tau that constant. And basically, the tau is subtracted to Zi. If the result is less than 0, then we truncate it to 0. Okay, so this is not a heuristic. This is exactly the rigorous solution of that optimization problem. It doesn't mean that we have a closed form solution for Sparse Max, because we still need to find tau, and tau is not arbitrary. Okay, so tau is a normalizing constant that is going to ensure that the sum of all these things is going to be 1, which is going to make P a well-defined probability distribution. And so the only hard part in evaluating Sparse Max is to compute tau. Okay, and I'm skipping details. You know, you can take a look at the paper if you want to see more. But this is something that we can do in linear time. So we can do it in O to the k. K is the dimensionality of Z, which is exactly the same costs, the same asymptotic costs that we have in Softmax. Because if you want to compute Softmax, you need to touch every component of the Z vector. So here, asymptotically, it's the same. In practice, it's a little bit slower. So the constant inside that O notation is worse than what we have in Softmax. But in practice, it's not a lot worse. And we have a lot of experiments that compare run times between Sparse Max and Softmax. So on the other hand, the gradient of this transformation, and again, if you want to see the full math, you need to look at the paper that I first mentioned. The gradient of that transformation has a very simple form, and we can compute it in sublinear time. Sublinear means that we might not need to look at all the components of Z to compute the gradient. And the reason why this happens is that if we apply a Sparse Max transformation to Z and you get a P where some components are 0, the gradient for the components that are 0 is 0. So you don't need to explicitly compute it. Okay, so you only need to worry about the non-zeros. So if you, for example, suppose that you are doing a Softmax over a vocabulary, like 50,000 words. If there's only 10 words with non-zero probability, doing the backpropagation step is only going to cost you a factor of 10, not 50,000. Of course, you need to cache the result of the forward step for this to be possible.
So if we use the Sparse Max over the vocabulary, isn't it that it's going to be just like the point where it's from the formulation, I get that it's a word that has a lot of probability and then just softening of the distribution around it. So the intuition of using it in the vocabulary, wouldn't it be like the word with the most with the most probability and the words around it, but in the vocabulary doesn't make that much sense?
So we're going to see some examples about how we use Sparse Max over vocabulary, but the intuition is that suppose, for example, that you are generating for machine translation, for example. Suppose that, so what happens if you use Sparse Max instead of Softmax is that only a few words are going to have a non-zero probability. All the others will have 0 probability.
Yeah, but isn't it the word with the most probability and the words around it in the vocabulary?
What do you mean the words around it? I didn't get that part. Like the semantically similar words, like words that have similar embeddings?
Yeah, because of the formulation of Sparse Max, that it's kind of just softening around it so that it's not just almost anywhere, everywhere non-differentiable.
So yeah, in practice, if you assume that you have like a bunch of word embeddings, what's going to happen if you use Sparse Max is that you're going to have like a non-zero probability for a word which is the highest scored, a few words in the neighborhood of that word in that embedding space, and all the others will be 0. While with Softmax, there's still some probability mass being assigned to everything else. So they might have a very small probability, but this probability is going to add up. So there might be like a long tail of probability mass being wasted to words that are very unlikely.
Okay, thanks.
I think this is going to become a bit more intuitive as I will go through different applications of this. Okay, so let's visualize what Sparse Max looks like and compare it to Softmax. So if you go to 2 dimensions, one classical result is that the 2D Softmax becomes the sigmoid function, the logistic function, right? So basically in 2D, Softmax just looks like this blue sigmoid. Okay. So on the other hand, Sparse Max, with the same choice of Z, will become piecewise linear, like this. It's like a hard version of the sigmoid. So the asymptotics are the same. It saturates on 1 and it on 0. But it has this exact saturation. Okay, so with Softmax, it's never 0 and it's never 1. With argmax, there's a value of t below which or above which the saturation occurs exactly. And in 3D, it's pretty much the same thing. Okay, so this is what Softmax look at 3D, and this is what Sparse Max looks like. So the asymptotics are the same. Okay, so the only difference is that this is piecewise linear, and there is exact saturation. This kind of explains why these transformations are sparse. So if you land in this region or this region, then we are going to have some 0 components. Is this intuitive? Okay. So there's a lot of other properties. I'm just going to summarize 3 that are in common between Softmax and Sparse Max. So if z is a vector of zeros, or a constant vector, then both Softmax and Sparse Max are going to result in a uniform distribution. Now, this is a nice to have. If we start with a certain z and multiply it by a constant t, we can regard this t as kind of an inverse temperature parameter. For those of you that are used to convert, to approximate argmax by a softmax with a small temperature, this is something, for example, that arises in Gumbel softmax. If we use softmax, then as t goes to infinity, this is going to become a delta distribution. For sparse max, we don't need to take the limits. So there is a finite value of t above which this transformation becomes a delta distribution. So this means that if I'm holding a simplex, there is a point above which, when you are moving z farther and farther away, there is a point above which it's going to hit a corner of the simplex. And the third property is that both transformations are invariant to adding constants. So if you add one constant to all components, then the transformation is not going to change. Okay, so in the original paper, the first experiment that we did was to apply Sparse Max for SNLI, natural language inference. I don't know was this problem covered in the school? No? Okay, so the task is we are given a hypothesis and a premise. For example, the premise can be a boy rides on a camel in a crowded area while talking on his cell phone, and the hypothesis is a boy is riding an animal. And you need to classify this relation as contradiction, entailment, or neutral. Okay, so contradiction means that there is a contradiction between the hypothesis and the premise. Entailment means that the premise implies the hypothesis. And neutral means that there is no relation. We cannot deduce the hypothesis from the premise. And what we did here is to replace soft attention over the premise words by sparse attention. And by doing that, we still produce a decision, but then we can look at the words that get selected, the words that get non-zero probability, and try to understand what are the words that are relevant for coming up with that decision. And if you do that for these examples, for example, for the camel example, then we end up getting non-zero probability on the words rides on and camel, which kind of justifies the entailment relation. And for the other examples, we get these words selected in blue that are kind of good cues that justify the final decision that we are producing. In particular, the last one is interesting because it's a very long sentence. A man wearing a yellow striped shirt laughs while seated next to another man who is wearing a light blue shirt and clasping his hands together. But in order to identify that this is a contradiction relation, there's only these words in blue that are selected. So which means that there's a lot of words that are irrelevant for coming up with this contradiction relation. Yes?
Have you compared them to the softmax exactly? Because usually when you make softmax, you could also see which words were important and they get highlighted. Is there such a big difference, and will there be more sprinkles around other words?
Yeah, that's a good point. So if you use softmax, typically you get like a number and then you threshold that number If the number is below 0.01, you just say, okay, this seems to be relevant because the probability is too low. So we did some visual comparisons between Softmax and Sparse Max. Typically, the Sparse Max probabilities, so we get exactly zeros, right? And we get like less distortion on the words that are more probable. And I think the reason for this is that Softmax defines applies the exponential function to the scores, which means that this is going to amplify the difference between the largest, the most probable words, while Sparse Max applies a linear transformation of the words, so it doesn't amplify that difference so much. Just a detail. But other than that, yes, Softmax will give something similar. I will just argue that this is kind of a more natural way of having something inside your transformation that is able to decide if it's going to select or not, instead of being someone setting up a threshold and tuning it.
Could it also be that the network is going to learn even better because you're restricting it? Like you're putting the network has to learn several things and to really infer from them? Any thoughts about that?
You mean if the accuracy is going to be lower because of using
higher.
Sparse Max?
Higher.
Higher? Because
if you let it train longer and then it really has to learn the reasons why he's wearing a blue jacket or not wearing.
Okay, so in this particular task, we didn't observe differences in accuracy. So basically what happened, if I recall correctly, is that we got slightly better performance in the dev set, but, the opposite. So we got slightly better performance on the test set, slightly worse performance on the dev set. So it's, we didn't observe differences in accuracy. For the other experiments that I'm going to talk about in machine translation and so on, you observe that the network seems to be learning faster if some components of the network use either sparse attention or sparse outputs. I'm going to talk about that in a while. Okay, so Sparse Max. So I presented here this example of Sparse Max in the attention, but we can also use Sparse Max as a loss function in the output layer. Something that replaces the logistic or the cross entropy loss. However, there is a problem if you try to do that directly. If you take log of p and p is sparse, this means that we're going to get some log of zeros sometimes, right? And this might make the log likelihood become minus infinity. If you are used to language modeling, then this corresponds to having infinite perplexity if you try to compute the probability of the next word that you're going to observe. So we cannot use the same log probability, the same interpretation in terms of log likelihoods. But there is a very natural loss function that arises with Sparse Max. I'm not going to talk about that in detail. Inspired by something called Fenchel-Young losses. This is a more theoretical paper that we have in a statistics conference. And we can derive a loss function for Sparse Max that is rooted on this theory. And this is what, every time I'm talking about using Sparse Max in the loss, this is the loss function that we're using. So I'm just removing the math from there. So this is the paper that I was alluding to. This was a AIStats paper that shows like a big class of loss functions. I think I have a slide later, but I might skip it. Showing that there is a natural choice of loss functions that includes the cross entropy, but it also includes something else that is interesting for these sorts of sparse transformations. So this, if you remember what I said in the beginning, when I introduced argmax and softmax, and then Sparse Max afterwards. We saw that argmax corresponds to maximizing a linear objective function, constraining the distribution P to lie on the simplex, right? And we also saw that Sparse Max corresponds to having a regularizer here that is a quadratic regularizer, so the L2 norm of P. It turns out that we can also do the same thing for softmax. And the question is, what is the regularizer that corresponds to softmax? It's an entropic regularizer. Okay, so if you pick omega of P equal minus the entropy of P, the Shannon entropy, then the solution of this problem becomes the softmax of Z. So the solution is P equals softmax of Z. And this is neat because we can actually look at argmax, softmax, and sparse max all solving a regularized argmax problem. So we denote that by argmax sub omega. And by different choices of regularizer, we can obtain slightly different transformations. Some are extremely sparse, like argmax. It's kind of extreme, the most extreme sparse you can be. It returns a one-odd factor. Others are somewhat sparse. That's the case with Sparse Max. And others are never sparse, which happens with Softmax. But still, we have these three different points. One thing that we were looking for is maybe we can come up with a parametric family, with one hyperparameter that for certain choices of that hyperparameter you can obtain each of these three transformations. And this is basically what we studied in the Fenchel-Young losses paper. And we came up with an interesting relation between these regularizers and something called Tsali's entropies. So Tsali's entropies were developed by a Greek physicist called Konstantinos Tsalis. I don't know if any of you is familiar with the name, but the reason why they were proposed is rooted in statistical mechanics. So we don't have the same intuition here, but it's basically a family of entropies that is parameterized by parameter alpha, where alpha needs to be greater than or equal to 0, and the entropy of a distribution P is written this way. And so it's not obvious, but if you take the limit alpha going to 1, you get a 0 here, and you get pi. So you get a sum of pi raised to 1, which is a sum of pi, which is 1, which means that 1 minus 1 becomes 0, and you get a 0 divided by 0 indetermination. But if you apply rules to solve these indeterminations, we end up with an expression for that, which becomes Shannon entropy. So this means that when alpha is 1, this becomes exactly the entropy that we're used to, P log P. And you get other interesting things for other values of alpha. So if alpha is 2, then what we get here is 1 minus the sum of pi squared. So this part becomes the squared L2 norm of P, and this becomes minus 1. And this is going to be, it's going to be related to the Euclidean regularizer. It corresponds to another entropy called the Gini entropy. And finally, if you make alpha goes to infinity, the solution of this is going to correspond to argmax. So this is what we decided to study further, and we defined this transformation. We call this transformation alpha entmax. This was a paper that we presented recently at ACL. So entmax, when alpha is 1, becomes softmax. When alpha is 2, becomes sparse max. When alpha goes to infinity, it becomes argmax. But now we have like a parametric family parameterized by just one number, alpha, that kind of defines how sparse we want to be. So, I'm skipping the mathematical details, but so what we did in this paper is that we defined the forward pass for arbitrary alpha. And so it turns out that the algorithm that computes that forward step is a little bit more complicated than the one that we use for Softmax and Sparse Max, but we can still do it with a bisection algorithm that is efficient enough for practical usage. And the backward pass runs in sublinear time. So again, one thing that we found out that is interesting is that for all values of alpha that are strictly greater than 1, the solution of that problem is always going to be sparse. So it's not just Sparse Max. Even if you have alpha equals 1.5, the transformation is also going to be sparse. Actually, the only value of alpha that is not giving a sparsity is alpha equals 1, which is what corresponds to softmax. I found this very extremely interesting. And another thing that happens is that the sparsity increases with alpha. So as we make alpha bigger and bigger, the transformation is going to become more sparse. So it's kind of similar to what you might have seen with temperature parameters, where we try to kind of smoothen argmax. But this is a little bit more stable than what we get with the temperature parameter, and I'm going to show some examples of that. So one particular case that we like a lot is 1.5 entmax, which is completely novel. It came out from this analysis. And there is a specialized forward pass algorithm that makes all the computation with 1.5 entmax extremely efficient, and you have that in a package in PyTorch, and I think someone else already did a package for TensorFlow in case you guys want to try this in practice. And yes, and in 1.5, Nmax just happens to perform very well for some tasks. Okay, so I'm going to skip that part. The gist of this is that for every choice of alpha in this Nmax, you can also define a loss function, which is kind of a generalization of the cross entropy. And this is a particular case of something called essential Young loss. So it's easier just to show some plots. Okay, so this is how the entropy looks like for different values of alpha. So alpha equals 1, the blue line corresponds to softmax. It corresponds to the usual entropy that we know. And the other values are bigger than 1. And this is what the, let's say, attention distribution looks like in 2D. So in the case of softmax, you get the logistic loss. You get the sigmoid transformation, the logistic function. For the green line corresponds to Sparse Max, what I had in the previous slide. It's kind of a hard sigmoid. The others, they are kind of more round, but they still hit 0, so they are still sparse. It's hard to see that in the plot, but this, for example, if you look at the yellow line, it's becoming exactly 0 after this point, and the same thing happens for any alpha greater than 1. So there's also an interesting relation between that and margins. If you look at the loss version of these alpha and maxes, so they also have something similar to what we get with SVMs, margin separation property, where the loss is 0 if you are separating points above a margin. You also get that for free with these transformations. Okay, so this concludes the first part, and I'm a little bit lost in time. I don't know how much time is this kind of. Did I took like 2/3 of the lecture, more or less? What? 20 minutes until the end? Okay. Okay, so I might skip this second part. So I'm just going to be very fast through it. So this is kind of some other stuff that we build upon Sparse Max that puts constraints on top of Sparse Max. So there are 2 papers, one at MLP and another at ACL about that. Let me jump to the usage that we got. So in this case, constraint Sparse Max. So the definition is exactly like Sparse Max, but we have an additional constraint that says that each entry in the vector P is upper bounded by a vector U that is given. So this allows us to put like a budget of how much attention each word can receive. Okay. And why do we want to do this? So we use this to model fertility in neural machine translation. So for those of you who come from the statistical MT words, there was all these models developed by IBM, and IBM Model 2 had this notion of fertility that is basically the number of words in the target that a source word is aligned to. And one thing that we noticed, in early usages of neural MT models is that they tended to do a lot of repetitions. Which means that if you look at where the attention is being, where the model is attending to when it generates those repetitions, it tends to look over and over to the same words. So we can control that by putting an upper bound of how much attention a word can receive cumulatively. And then we can use constraint Sparse Max to make sure that we don't put too much attention to particular words. So this is what we did. The details is that we can just plug and play these transformations in a neural MT model. It's still efficient to do the forward pass and the backward pass. And this is a practical example of what we achieved. So this is an example of a translation by using softmax attention, where there was this repetition. So this is the last 100 years law of the last 100. And by using constraint Sparse Max, we don't get that repetition anymore. And in general, in the corpus, we observed much fewer repetitions by doing that. This is another example where the word government gets repeated. Yeah, so there are some sentence examples. You can always take a look at the slides later if you want to know more about this. Any questions? Someone was raising the arm? No? Okay. But yeah, so this was an interesting application. We didn't gain a lot in terms of blue, but we observed better properties in terms of over-generating or repeating words. So there is another line of work that I'm not going to talk about today called Sparse Map, which is a generalization of Sparse Max for structure prediction. So if you remember Xavier Carrera's class, he was talking about CRFs, structured SVMs, I guess. Did he cover that? Okay. If you look, for example, at the CRF, that model is not sparse. It's going to assign some probability distribution to every element of this structured output space, which is exponentially large. So we cannot enumerate, for example, if you are doing parsing, there's kind of a prohibitive set of possible parse trees that correspond to a sentence, and we cannot enumerate what are the ones that are that have non-zero probability. But with Sparse Map, we can do that, and we have a bound about how many parse trees can be, the solution of Sparse Map. That was the main motivation. We can use that both in an output layer, but we can also use it as a hidden layer. So we can also consider syntax as a latent part of the model and try to do, for example, machine translation, but conditioning on a small number of latent parse trees, for example. So if you, I don't know if Xavier mentioned that, but if you try to kind of define the correspondences between what happens in the unstructured case and the structured case. So in this structured case, we have argmax, where you want to pick the configuration with the highest probability. In the structured world, this is called maximum a posteriori inference. So it's basically a single configuration that is the most probable. When you have softmax, the corresponding thing in structured prediction is marginal inference, computing expectations. And in the case of Sparse Max, the corresponding things in the structured world is Sparse Map. And we applied this to some problems in natural language inference by using different forms of structure. So I'm going to skip that. So this is an example where for a given sentence, using a Sparse Map in the output layer, we came up with a probability that only gives non-zero probability for two parse trees, two dependency trees. So one where edges is as the word looks as the head, and the other one where edges is attached to Brown. Every other parse tree gets zero probability. So this might also be good to preserve some ambiguity that we are not sure how to solve. And there's a lot of related work, inspired by this. I'm going to skip that part, and I'm going to jump to sparse sequence-to-sequence models, which is an application of Sparse Max in RNN-based models with attention. Any question before I go to that part? Yes?
Can we understand the alpha and max as a hyperparameter that controls the sparsity of the predictions?
Yeah, so you can look at alpha so far from taking into account what I already said in the talk. You can regard alpha as an hyperparameter, and that hyperparameter is controlling how sparse either the prediction is going to be if you use it as an output layer, or how sparse attention is going to be. Correct. So in the last 5-10 minutes of the talk, I'm going to talk about the case where you learn alpha. So it's no longer an hyperparameter.
Did you use some special techniques for the initialization of the weights in the Sparse Max level?
Yeah, that's a great question. So, that was one concern that we had in the beginning. In practice, it never happened, which is good. So the concern is, since the gradient of Sparse Max, if you have scores that have high variance, the gradient could be 0, and then the model cannot learn anymore. We were concerned that if we didn't initialize in a smart way, we could just fail learning. In practice, that never happened. So we used the same initialization that we use for Softmax, both in the attention mechanisms and the output layer, and we were always fine with it. Yeah.
Could you just comment in general for all of these sparse components? What are the gains in terms of performance metrics for the models using them?
So I'm going to talk a little bit about that in this part. In general, sometimes we observe some modest improvements in accuracy. We never observed with these techniques that I just presented huge gains, but we have other benefits. For example, in the case of the constrained Sparse Max that I was showing, we get a lot less repetitions in machine translation, which is something that Blur doesn't capture properly. Accuracy is a bit overrated. We can also interpret things a little bit better with Sparse Max. We can argue that, sure, we also get that with Softmax if you truncate your probabilities. It's true. I just found this like a more natural mechanism of a transformation that is built in to learn to choose what is relevant and what is not relevant. But we never got worse performance than Softmax. The worst was matching Softmax performance.
Thank you. I'm not a fan of just optimizing for performance metrics, but just for information. Thank you.
Mm-hmm. Okay. Right. So this was a paper that we presented at ACL this year with my student Ben Peters and Vlad Nicolai, who was a postdoc in my group. So the backbone model that we used was an RNN-based model with attention, and the key idea was just replace all instances of softmax in that model by either Sparse Max or alpha and max for different values of alpha. So there's basically two instances of softmax that we have in the RNN model with attention. We have one in the attention mechanism, and we have one in the final cross-entropy loss, the final output layer. So we replaced both. So you consider sparsity both in the attention mechanism and in the output layer, and we looked at two tasks. One, machine translation, where units are words, and we also looked at a simpler sequence-to-sequence task that we can address with the sequence-to-sequence models, which is morphological inflection, where we are given a lemma as a sequence of characters. We are also given some inflectional tags, like a verb, second person, present. And the goal is to generate the inflected form of that lemma using those inflectional tags. And this is a character-based task. And so just to give you a gist about what this biases in terms of machine translation, this is showing the sparsity that we get in a forced decoding regime. So this is basically, so we went through the validation set. We know the goal translation, the reference translation. It's basically the words that are in bold here. And we looked at what was the probability that was assigned to all the words for each time step. So we always condition on the reference context, and we just wanted to see what is the probability distribution that the model is assigning to the next word. And so in this case, in the first time step, there was only 4 words with non-zero probability. Everything else got exactly 0 probability. Then for the second and third words, these two both got probability of 1, which kind of allows us to autocomplete, right? You can just generate the 2 words immediately. And so on and so forth. So in general, we can see that very few words get non-zero probability with this model at each time step. We have this interesting property of autocompletion when you have consecutive words that the model is very confident about. And of course, it's not realistic if you're doing machine translation, it's not realistic to condition on the correct reference. But if you think of this as something that can be used in an interactive manner, where you have a human translator that is working with the predictive translation system, so the system generates hypotheses and you just need to select one, then this can be very useful. Okay, so we are not setting like a maximum number of possible continuations of the sentence. This is learned by the model. So the model knows exactly how much words are going to have non-zero probability. So this is something that we can do with sparse transformations that you cannot do with softmax. So any question about this task? Okay. And so we looked at what was the impact of these sparse attentions of these sparse transformations, both for the attention mechanism and the output layer. And what we observed is that using sparsity in detention, for different values of alpha, recall that 1 corresponds to softmax, 2 corresponds to sparse max, and we have some interesting things in 1.5. So in terms of using a different value of alpha for the attention, it really didn't make a very big impact in final blue scores. It stayed essentially the same. But when used in the output layer, we observed, very consistent gains, and this was done so the plot is for one language, but if you look at the paper, we have results there for, I think, 4 different language pairs in different directions. And you observe very consistent benefits from using values of alpha that are different from 1. In particular, this region, slightly below 1.5, and including 1.5, seems to be beneficial in terms of accuracy. So this represents, a gain of 1.5 or 2 blue points. I don't know by heart. So in the case of attention, we don't observe gains in accuracy. We can claim that our alignments are more interpretable. We can list down the alignments that get non-zero probability. But for the loss, it's immediately useful in terms of getting better performance. And so one thing that you might be concerned about is, okay, but maybe that comes at the cost of increasing computation time. So one thing that we find out is that, and this is just a comparison between softmax and 1.5 entmax, which we found to perform particularly well. If you look at how many seconds of training it takes to get top performance, 1.5 entmax, becomes more accurate a lot faster. And so these consecutive timestamps is basically the difference, how much slower is 1.5 entmax compared to softmax, which is a tiny bit. Okay, so it's not something that is very harmful. So the other task that we considered here was morphological inflection. Just to give you a gist about what that task is about. So you are given. Okay, so this is just showing possible inflections that the model generates. And what it tends to do is that it's usually extremely sparse. So since the space of characters for the languages that you considered is much smaller than the space of words, the vocabulary size, we tend to have only a few sequences, complete sequences, with non-zero probability. We don't get that for machine translation, right? So there we get sparsity for each time step, but here we get sparsity for the full sequence. And this is neat. So basically for one example where I guess the input was lemma, draw, and the inflectional tags were past participle, something like that in English. We get a model that assigns 66.4% probability to draw, which is wrong, by the way, and some probability to drawn, some probability to draw, but for everything else, there's 0 probability. So there was one time where by accident, we kind of had a bug in the system where we forgot to specify the inflectional tags, and the output generated the full paradigm of the word, which was neat. So we still need to kind of make more rigorous experiments in that front to see if this happens in general. But this is something that we can obtain just by looking at the entire set of strings that have non-zero probability and try to understand what that set means. So we have a follow-up variants of these models that we used in the Sigmorphon share task. I'm going to skip that, but there are some additional interpretability studies that we conducted with these models. And now I have 3 minutes. So I'm going to quickly kind of present this work that that is going to appear in MNLP, Adaptively Sparse Transformers. This is joint work with my student Gonçalo Correia and Vlad Nicolai, a postdoc in my group. And we already learned about transformers, so I'm not going to bother you again with that. The relevant part is these equations that you have both in self-attention, both in the encoder and decoder, and in contextual attention, where we need to do a certain computation involving keys and queries, and then we do a softmax, right? So what we are doing here is to replace the softmax by alpha entmax, but but we're also going to learn the alpha. So this is why we call it adaptively sparse. So we are going to have one alpha parameter for each attention head at each layer. So if you have like 6 layers with 8 attention heads, which is kind of the basic transformer model, then we have 48 different values of alpha that you want to learn. So you just consider all those things as parameters that you want to learn. You can regard this alpha kind of similar to a temperature parameter, but more stable. So we could never do this if you were trying to learn a temperature parameter or 48 temperature parameters for each attention head. So yeah, actually we tried to do that and it failed. But it worked when we tried to learn alpha. And let me show you the results of some analysis that we did. So before that, there's a kind of, at the same time that you were working on this, there were a few papers that came out that were also proposing sparse versions of transformers. So this is how our work relates to the others. So one of them is the sparse transformer that came out of OpenAI, where they basically consider a fixed window. So the sparsity comes from the fact that they are not attending to the entire sentence, but they have like a fixed sized window that they are going to attend over. There was another work, a nice work presented at ACL, developed at Facebook, that they call adaptive span transformer. It's also adaptive in the sense that they learn how big the window should be. So the difference is that they always assume that this is a contiguous window. Okay. So what we are doing differently is that we allow the window to be non-contiguous, and we learn like a different alpha parameter for each attention head. So this is basically a description of what our sparsity pattern could look like for different attention heads. Okay, so one thing that we observed was what were the trajectories of these alphas during training. And so here we are showing different layers and different attention heads in different colors, and we are tracing what are the values of alpha that they get through training. So it seems to be a tendency. So remember that 1 means softmax. So the normal transformer is basically alpha equals 1, and 2 is sparse max. So there seems to be a tendency, if we randomly initialize all the parameters, there seems to be a tendency first to become a bit denser, to make sure that you are attending to enough information. But after a certain point, that happens relatively early in training, the attentions start to become sparser and sparser. Some more sparse than others. Some of them become very sparse very quickly. Others prefer to stay dense. But it's interesting to observe how these things are learned from data. So another thing that we found out is that the optimal alpha after training, we draw some histograms. So we constrain alpha to be always between 1 and 2, by the way, between softmax and sparse max. So we observed that for the encoder, there were like 2 modes. So there are some attention heads prefer to have dense attention, but there's other attention heads that prefer to have more sparse attention. In the case of the decoder, both in context attention and the decoder self-attention, they don't have this second mode, so they are not too sparse. They are a little bit sparser than what we will get with softmax, but not too sparse. And we also looked at the head density per layer. I'm going to skip that because we don't have a lot of time. So there's a lot of analyses that we... Oh, this is a simple one. Okay, so I need to fix that in the slides. So we looked at several things. For example, how much dense attention heads are, meaning like what's the fraction of words in the source that they attend to per layer. And we observed that this varies a lot across layers. And we also looked at how much attention heads disagree with each other. And this is something that we can measure by using the Jensen-Shannon divergence, which is a divergence metric that compares different probability distributions. We also looked at what each individual head is doing. So there is another nice paper at ACL from Elena Vojta and other people where they try to characterize the different attention heads. This is related to what they found there. We saw that these behaviors are much more pronounced if you used alpha and max than if you just use the regular softmax. So there's heads that detect just a 10 to the previous position. There are heads that looked at question marks, or they looked if the sentence is an interrogative sentence. There are heads that try to merge BPE subwords, and we can find very interesting examples of that. So I think time is over. So just to conclude, so I started by motivating this work by looking at the building block of how do we define a transformation between real numbers, vectors of real numbers, and probability distributions. We came up with several transformations that have this property of being sparse. They can also be constrained, or they can learn to prefer certain kinds of structure. All the tensions, all the transformations that we define here are differentiable, so we can plug them in a neural network and get an end-to-end differentiable model. The gradients are always efficient to compute. They can be used either as hidden layers or output layers. We saw in these last few slides that we can also adaptive how sparse the attention should be. And we have come up with several experiments, both in RNN-based and transformer models, where we got somehow like improved accuracy for the first set of experiments, if you used it in the loss, and better interpretability. So this is it. Thank you very much. So.